Welcome everybody, and thank you for joining our Brain Vision Analyzer 2 webinar, Analysis of Event-Related Potentials. My name is Michael and I'm happy to be your presenter today. My colleagues Lisa and Michael have joined me as our moderation team. Before we start, what are the intended goals of this webinar? First, I'd like to introduce today a couple of transformations in Brain Vision Analyzer 2 that might be useful for your own ERP analyses. We will have a look at those transformations that are most commonly used. Second, I will demonstrate these transformations based on two classical cognitive paradigms. Therefore, most what you will see today will be shown directly in Analyzer while working on real data. What I hope you will take home from today's session is that for once you get an overview of important tools for ERP analysis, and also that you learn how to extract data from Analyzer for your statistical analysis outside of Analyzer. Please note, though, that the pipelines I will show today are just examples and do not claim to fulfill any recommended standards. Of course, they are based on scientific practice and guidelines, but I want to point out that every dataset is different, and therefore also every analysis is different and needs to be adapted to the requirements of the data. Let's have a look at today's contents. I will start with a very brief introduction of what are event-related potentials. To begin with our practical demonstration, I will construct a whole processing pipeline with you for an auditory oddball paradigm. The aim of this analysis is to get a P300 ERP component. I will demonstrate some common pre-processing steps, and I will show the difference between discarding blinks versus correcting them. In the end, I will detect the P300 peak and export key parameters. Afterwards, I will switch to another paradigm, which is a cross-modal semantic priming, aiming at an N400 ERP component. I already prepared the data analysis of this part, as I want to focus on a single step within this pipeline, which is how to make use of advanced Boolean expressions to achieve more complex segmentations. I will finish with showing you how to create a grand average. At the end, we will have our usual questions and answer session, where we invite you to ask your open questions. I will conclude with some recommendations for further reading. To get everyone on board, I discuss briefly what an ERP is and where it comes from. How do we get from the continuous EEG oscillations to the ERP waveform? As the name implies, an event-related potential represents activity which is evoked by a certain event. Or in case of a controlled experimental situation, this event is presumably some stimulus. Usually, you would have many more stimuli of a similar kind, thereby repeating the presentation or stimulation over and over again. You end up with a certain number of segments or trials. However, you need to consider that each trial within your EEG recording consists not only of the evoked activity, but also of ongoing EEG activity or noise. What is basically done to get to a representative waveform of this evoked activity only is to take all trials in reference to the same type of stimulus and then average across trials. And what I get after that is the ERP waveform, where the ongoing activity or noise should be cancelled out due to the averaging, and I get only the evoked response. Now that we roughly know why we see such a nice waveform in the end, after we average dozens of trials, let me show you a little bit more. In this butterfly plot, every time course reflects the ERP of an individual scalp channel. ERP components are reproducible positive or negative deflections from the baseline, often called N100, N200, or P300. The latter refers to polarity and the numbers refer to rough latency. Hence, the P300, or P3 in short, refers to a positive deflection around 300 milliseconds after the stimulus. Note that ERPs are by convention often plotted negative up, like here, which means positivity is reflected downwards and negativity is pointing upwards. The two main features of an ERP that you could quantify is the amplitude and the latency of a component. Topographic maps nicely show the spatial distribution of ERP components across scalp electrodes. In this example, you can see, for instance, that the P100 is more left parietally located, whereas the P300 shows a widespread frontomedial distribution. Now that we reviewed some basics, we can jump right in and check some real data. I will mostly go through an example pipeline with you that we will build up step by step in Analyzer. Today's first example, I will analyze a dataset from an auditory oddball paradigm. An auditory oddball is characterized by frequently appearing standard tones and rarely occurring target tones, which are often called deviants. These deviant tones usually require a response, for example by pressing a button. It could be that standard and deviant tones are only differing in pitch, like a low-pitched standard tone and a high-pitched deviant tone. However, there are many more experimental manipulations possible. What can usually be observed is that the P300 ERP component is stronger for deviance, what you also can see here in this example on the right. The amplitude varies, for example, with the probability of target appearance, whereas the latency varies with detection complexity of the target. But also here there are many more observed effects due to the selection of stimuli or presentation scheme, which were investigated in thousands of scientific studies. Let's switch now to Analyzer. As you can see, I have a couple of data sets in my workspace, and I will use the first one for this part of our webinar. I have also the online info open here where you get information about new things around Analyzer. I will close that for now. And I will open instead the raw data of my oddball subject 1. In case you don't know yet how your data set looks like, or how, what channels are in there or whatever, a good thing to start is to check the properties of the data set. So I click on raw data with the right mouse button and I select properties. Let's stick to this overview tab here. What you can see in here is the number of channels. It's 32. These are scalp channels, but also including 4 EOG channels and also the left and right mastoids. You can also see here the sampling rate, which is 1000 Hertz, and you can see the length of the data set in data points and in seconds. This data set has a length of about 220 seconds, so it's very short. It's just less than 4 minutes. What we cannot see in here is the recording reference, but I can tell you it was FCZ. In the next step, let's check our markers, as they are crucial for an ERP analysis. They can be checked again via right-clicking on raw data and selecting markers. In this table here, I get an overview of all markers that are in the data set. And I also get, besides the name and the type of the marker, a count. Our oddball paradigm consisted of 100 stimuli with 30 deviants and 70 standard tones. Therefore, only these two markers can be the ones that are referring to deviants and standards, respectively. There are a few other markers in here, but let's forget them for now. In this data set, actually, we do not have responses recorded, therefore no markers for that. Okay, I checked now my markers of interest. They are there, and more importantly, all of them are there. But now I want to make it a bit more intuitive and rename my markers, as S21 and S22 are not very telling names. Therefore, I close this marker overview. And now I want to change my markers, and this can be done with the transformation edit markers. As you probably know, to apply a transformation in Analyzer, you have always to activate a data set so that it's shown in the display. Then I go to Transformations tab. Most of the things that we use today you can find in here. And then I go to the Others group at the end. This is not fully shown here because of my display. And in here, there's Edit Markers. Okay, edit markers has 3 modes of operation. Because I want to change the names of all markers, S21 and S22, I use the automatic mode. In here, you can select the marker that you want to change by giving the marker type and marker description. Therefore, I will use this here and select stimulus for the marker type and select S21 as the marker description. And now I can down here for new marker description enter a new name. And S21, that was my deviance. So I will just write in here deviance. And then it's important that you click add, so it appears down here. The same I do now for the S22 markers, same type, and the new name will be standards. And again, it's important that you click add. Here you can see now what changes are going to happen. I click finish and I get a new node, edit markers. And if I now scroll in the data a little bit, then you can see here that my markers are now called standards and deviance. Okay, let's scroll through the whole data set, which is fairly short and therefore will go fairly quick. A visual inspection should always cover certain things, like that you're looking for artifacts, that you're looking for bad channels, that you're looking for channel drifts, and of course the marker placement, what we just did. Okay, as you can see, this data set seems to be fairly clean, so I do not see any huge artifacts, just some noisy portions, like here, for example. And I can see some, go back to the middle of the data. Yeah, here, for example, I can see some EOG related artifacts. There are blinks. You can see them down here where my EOG channels are, but you can also see them up here in my frontal channels. Okay, this is a very short data set, of course. Visual inspection is therefore very quick. However, I would recommend to always do this also for longer data sets, as your expert eye is invaluable to evaluate the quality of your data. Lastly, we want to keep our analysis tree tidy and telling, and therefore I recommend to edit the name, because always these default names are given. So I usually stick to the default and just enter a suffix in the end, for example, and I will call that rename S21 S22, because now I see on first sight what I have done in that node. I will do that throughout the analysis that I showed today. This is not only handy for the bookkeeping, but also quite important for analysis automation and analyzer. Of course, the operation infos that you can also find in this menu here, they give you the full information on what was done in each step, so you won't lose any details of the processing pipeline. Okay, let's now switch to the first real data processing step, which is almost always applied and often right at the beginning. And I am talking of filters. Please let me emphasize, though, that there is no such thing as a golden recipe. The processing steps used and their sequence highly depend on design, methods, and what I'm actually trying to achieve. In our example pipeline, I decided to filter first. So I therefore checked that the right data set, so the newest one, is selected and displayed. And then I go up to transformations, and the filters can be found in the artifact rejection reduction group. There is this data filtering drop down, and in here is IIR filters. This is a Butterworth zero phase shift filter, which is applied twice, once forward and once backward, to retain phase relationships. Let's select a low cutoff of 0.1 and also a high cutoff of 40 Hertz. So this means that frequencies between 0.1 and 40 Hertz should be passed and everything below and above should be suppressed. This is hence a bandpass filter, which is nothing else than a combination of a high pass and a low pass filter applied in one go. You probably saw already that the graphic here on the right was immediately changed when I entered my values in here. So this graphic is the filter response function of the currently selected filter. Digital filters cannot be perfect regarding the cutoffs, but they ensure a certain suppression level at these frequencies. So there is no straight division line between passed and suppressed frequencies, it's rather a gradual passage. You can see that very nicely in this filter response function, which has a rather shallow and long-lasting gradient towards higher frequencies. In case we want a steeper gradient of the filter function, we need to change the filter order. Let's change it to 8. And you see the immediate effect. I get a very steep slope now at the cutoff. Steep, yes, but still not a straight line. But it will ensure a little bit clearer suppression of at the cutoff frequency, so not such a shallow slope that the one we saw before. So we will not use any of the other filter options here today, but let me introduce you one more detail. As you might know, Analyzer works based on on-demand calculations, which means that only parameters are saved in your history files. Data displays are always constructed on the fly by applying the sequence of parameters to the raw data. So there's usually no new data set saved after I apply a certain processing step. However, sometimes it makes sense to save the data to a hard disk for performance reasons. For filters, we recommend to do this, and you therefore should enable this option down here, Store Data in Cache File. This will optimize the filter quality, and it is especially important if you use rather low cutoffs. For now, let's press OK. And we can now inspect the effect of filtering by scrolling again through the data, but we can also overlay the data from the unfiltered node and then scroll through it. And what I hope that you can see is that the higher frequencies, they are now much less pronounced. What is harder to see is the effect of the low cutoff. The easiest way to see this is usually to compare the amplitude levels in both data sets, because the filter should have removed any large offsets. Okay, I close the overlay, and to finish, I will just again rename my node, and I will call it 0.1 to 40 Hertz to see directly what filter I applied. What is next? I told you earlier that the data was recorded with a FCZ online reference. Depending on the effects you aim to analyze, the reference is an important choice. If you choose a reference close to where you expect the effect, you may not get any clear results, as the reference voltage is subtracted from all other channels. FCZ is likely to be affected by the P300 in our oddball paradigm, as the P300 is usually most prominent at midline sites from frontal to parietal electrodes. Hence, a different reference, which is further away from the electrodes of interest, may lead to better results. Often a linked mastoid reference is used. Linked means thereby the mean of the two mastoids, as we did not physically link those electrodes during recording. For re-referencing, I need to go to Transformations, Dataset Preprocessing, Channel Preprocessing, and in here I have the new reference transformation. Okay. Here I have all my available channels to select for the new reference, and I select A1 and A2, which is the usual name for the mastoid channels. So it is important now that I disable this option down here to include the implicit reference into the calculation of the new reference. Implicit reference means online reference, which was FCZ. We do not want that the voltage of FCZ is included in our new mastoid reference. Okay, I go to the next page, and now I have to select the channels where I want to apply my reference to. And I select all channels except for A1 and A2, which form the new reference. And I don't keep the remaining, so the unreferenced channels. And this means that my A1 and A2 that I don't reference are dropped after this transformation, because I do not use them anymore afterwards. Okay, in the last page of the dialog, you can give a new name to the reference channel. Here the default is AVG in case you want to do an average re-reference. You can enter whatever you want. I will not enter anything. If you enter something here, this name will appear in all data displays to the right of the channel label. This is especially helpful if you reference your data to more than one channel, because then you can see right away which channel is referenced to what. What I will use though is this option here, reuse old reference channel, and I will call that FCZ. Okay. By using this option, I will regain my online reference as a new channel. Please note though that this is not 100% the same thing as if you would record FCZ as a normal channel. It's rather an approximation by mathematical means, but it's a very commonly used option. I click finish and I get my new data, and you see that looks slightly different now. Okay, I will finish this step again with renaming my node, and what I will put there is mean mastoids. Okay, as we saw from scrolling through the data earlier, our data contains idlings and other artifacts. These can be rejected using raw data inspection. You find that up here in artifact rejection and reduction group. There it is, raw data inspection. This transformation has, again, 3 modes of operation. The manual mode can be very time-consuming, whereas the automatic mode is very quick. There's, of course, also a discrepancy between subjectivity and objectivity here. However, often a good balance between these 2 extremes is just right. We recommend, therefore, the semi-automatic mode. And next, I will have to collect my channels. One more word for the semi-automatic mode for those who don't know it yet. So it means after I click OK, I will get an interactive window, and in this window I can check what was automatically marked. I can also revise the parameters for the dataset and rerun it with new parameters, and I can also mark or unmark artifacts manually. Then I select the channels, as I said, and I will actually enable all channels. And then I go to the criteria. So depending on the data, you can adjust the criteria accordingly. Let me give you a brief tour what we have here. We have the gradient criterion, which can detect abrupt voltage steps that rise steeply, like spikes. We have the max-min criterion, which is very useful for high amplitude artifacts in DC recordings, meaning where you have an offset from 0. The amplitude recording is also useful for high amplitude artifacts, but rather in non-DC recordings, or when offsets from 0 have already been subtracted. And the low activity criterion finds intervals where for any reason no actual data was recorded, but only a flat line is shown above. What you can also see in every criterion is that you have down here the option to mark as bad before or after event. So here you can enter time intervals that will be marked as bad intervals, so as artifactual, before and after the data point where the criterion applied. You can see this like something as a safety margin around the artifacts. Let's keep it simple for today. So I want to only check for certain amplitude thresholds, which means I will uncheck the other criteria. I will only check that one, and I will go to a rather low value, -80 to +80 microvolts. These are rather strict settings, but here I want to show you what happens if you reject data for the sake of a clean ERP. I will show you another strategy later. Okay, I click down here now, okay. And now we are in the interactive window of the semi-automatic mode. We can scroll now through the data. We see there is some stuff marked. We can also see down here in the navigation bar, there are a lot of yellow patches in here, which means this is data that was marked. If the detection was for some reason not fitting the data, and there are either artifacts unmarked or way too much data is marked, you can now rerun the detection if you click on Change Criteria, adapt them, and rerun it again. The table below shows which kind of criterion led to an artifact at which data point and what channel. Now I only used amplitude criterion, so you will only see that amplitude here. But if I used more, it can also happen that you see multiple in here, which means that more than one criterion applied to a specific data point. Okay, for now I will just click OK and see what comes out. As you see now, we have a lot of red markers in the data now, which are the bad interval markers. This data is still there, but following transformations respect these portions and will not use them if the computation is not carried out individually for each data point. So if the data point would influence other data points. At this stage, the bad intervals won't be discarded, because if you would cut out the bad intervals, the data would jump at those time points and the continuous flow would be disrupted. Let's scroll through the data now once more. And I would say pretty much everything marked in red is due to an ocular artifact, yeah, like blinks here, or let's jump back. Here, for example, also there is eye movements. So if our goal now was to reject data that is due to ocular artifacts, this was done pretty nicely now, and we kind of got everything of that. So let's take it from here and go to the next step for now. I will adapt my node name, and because I mostly captured blinks, I will also call this reject blinks. Okay. As we are looking for the ERP, let's now segment our data according to our markers. As a reminder, our goal is to average in the end across trials within each condition. Okay, go to transformations, go to segment analysis functions, and there you find segmentation. Just a side note, if you're coming from another software, segmentation is often referred to as epoching, but it's one and the same thing. There are different ways to segment your data. Based on a reference marker, based on a fixed time interval, so there's no marker necessary, based on manually entered timestamps, also no marker necessary, or based on pairs of start and end markers. The first two will lead to segments of equal size, while the latter two can lead to segments of equal size, but they don't have to. I will select the create new segments based on the marker position option because we have reference markers. We renamed them earlier and we will use them now. And in the next page, I see already an overview of the markers that I have, and I see also my standard and deviant markers. And for now, I will select the deviants and I will click add and select it as a reference marker. And I see also the count again, it's 30, so I should get out 30 trials of it. Down here, you can see the advanced Boolean expression field. Let's forget about that now, but I will come back to that later. I click next, and now I have to give the times for my new segments. And I will use -200 to 800, which means I would get segments of a length of 1000 milliseconds. You can also select the length of the segments based on data points. Careful though, in this case you see the same numbers because my sampling rate is 1000 Hertz. But for example, if the sampling rate is 250 Hertz, you would see down here -50, for example, because -50 data points is equal to -200 milliseconds. I have two more options down here. The first one is allow overlapped segments. I will not use that for now. So this option would make no difference in my case actually, because overlap is not possible because my segments are 2 seconds apart, and I only selected them for 1000 milliseconds of length. This option can be useful though in very fast-paced paradigms where you still want to see some more data after the stimulus. If you do not enable this option in such cases, overlapping trials will be discarded instead. Then the skip bad intervals option is down here. I will also disable that. If I enable it, everything that has a bad interval in it later, so every segment with a bad interval, will be discarded automatically. But I do not want to do that for now. Just one more word to the time window that I selected. So I selected, of course, this negative number in front of here because I want some baseline for my intervals. And so this baseline, of course, needs some considerations. So it should be long enough, but it should also be short enough. And also the time for the whole segment should, of course, be long enough to cover all effects that you expect. Okay, let's for now finish and check what we get out. What you can see instantly is that you get a different view. This is the grid view, and it will show every channel in a little box, which has the dimensions of the segment length that we have now, so -200 to +800. And what you can see now or what you can see as well is the reference marker. So the deviant marker here is now at time point 0. We see down here segment 1 of 30. So we have 30 segments, 30 deviant markers, and we can now scroll through the segments one by one. You can easily identify that there are segments with bad interval markers, but you can also again see that down here that quite a few of them have that. And when I go through my segments, you can also see the index down here. So now I'm in 9 of 30. So you always know where you are. Okay, segments with these bad intervals can be easily seen, as I said. We kept them for now, but later in the average, they will be automatically discarded because the average doesn't want to take bad interval data into account. Okay, let's rename the node. Now, importantly, because this is our deviant condition, so this is the segmentation deviance. So now we have our segments. Does that mean we can now average the data to get our ERP? We could in principle do this. However, I want to first use a baseline correction. This step ensures that all trials are centered, meaning that offsets in the amplitude level between trials are discarded. This is done by taking the mean over the baseline period and subtracting it from every data point in the segment. Baseline correction can be found just next to segmentation in the segment analysis functions group. So as I mentioned earlier, the baseline period requires some thoughts. 200 milliseconds, for example, includes 2 full 10 Hz cycles of data, which makes it less likely that the ERP is influenced by strong alpha activity. This is why I already used -200 as a baseline in the segmentation. The pre-stimulus interval is then by default selected from by baseline correction. You can, of course, also edit it, but I could only make it shorter, but I could not make it longer because I can only go to times that are really there in my segments, and -200 is the earliest I can get. I will click OK. Good. And now quickly rename this again so we know what the baseline was. And now the last step before getting the single subject ERP is calculating the average. And the average again can be found in the same group, just next to segmentation and baseline correction. On the dialog, I see the available segments, 30, and I will use full range because I want to average across all trials. You can also just average across a specific range of segments, so like from 10 to 20. You can also enable odd-even averaging, like this, and only average odd segments or only average even segments. Yeah, I will not use any of these for now. I want to average across all segments. Just one more point. What you can do, for example, is also create a data set for standard deviation across trials. In that case, you would end up not with 1, but with 2 new nodes, the average, and below the average, the standard deviation node. I press OK. And here's my average. The first thing I do now is renaming it. So this is now my average to the deviance, which means this is my ERP to the deviance tone stimuli. Let's inspect the average waveform. I will maximize therefore one channel, and I will take PZ. Okay. I have in this view here now the positivity around 300 milliseconds. Actually, I have plotted now my positive amplitudes upward and the negative ones downward. Let's say now I want to follow what a lot of people do in their papers and show the ERPs the other way around. And let's switch it again. I do that in File, Preferences, Scaling. And here is this polarity positive down option. I will enable that, click OK, and then it swaps around. So now positive is downward and negative is upward. I do that just now to match the pictures that we have seen before because they were all positive down. Okay, so we have now this positivity here around 300 milliseconds. And what we can do now is I already marked this positivity and my transient view context menu opens up and I click mapping view. And what I get is this topographic map, which shows the time window that I marked. So it says down here not minus 217 milliseconds to 407 milliseconds. And what is shown is the average across this interval. And what I can see already is a nice positivity. It's rather parietally located, a little bit more to the right side maybe. And here I am at channel PZ. So there I'm pretty much in the middle of this positivity. Okay. In fact, we would now be done with the deviance and could repeat our analysis based on the standards. However, you might remember that we saw after segmentation that a lot of trials had a bad interval marker in them. As I mentioned, those trials are automatically discarded and not considered for the average. That raises an important question on how many trials is our ERP based. And we can easily check it if we go to the average node and check the operation infos. And here it tells me the number of segments used for average is 13. This is not very much because I had 30 trials, which means I lost more than half. So not a very good outcome. My ERP is just based on a few observations, and this could be criticized as being invalid. Also, such an ERP might be lacking statistical power when you enter the data into a subsequent t-test or ANOVA, for example. Let's therefore consider alternative options. The question is, where did we lose so many of our trials? And the answer is pretty clear: during raw data inspection, as we got a lot of bad intervals due to ocular artifacts. What are our options now? We could change the artifact detection criteria to detect less artifacts. However, this would lead to smaller blinks staying within the data. So if we raise the thresholds, this would be in the long run still contaminating our ERP, at least at frontal sides where ocular artifacts are mostly observed. We could also change our strategy, and instead of rejecting ocular artifacts, we could try to attenuate or correct them. And this could be done with Ocular Correction. So let me go back to the Transformations tab. You might know already we have two Ocular Correction tools available in Analyzer. One is ICA based and the other one is regression based. More specifically, it's based on the approach by Grattan and Coles. I will now focus on this latter one. You can find both here in the Artifact Rejection and Reduction group. The question is now, where do we apply Ocular Correction? We have to go back to the data in the back above in the tree. We could apply it here. No, that's not a good idea actually, because all my blinks are marked by the detection criteria. And as I mentioned earlier, the bad intervals will not be considered by many transformations. And here, the data in the bad intervals would be harming the calculations. Therefore, they are not considered. But we need to consider them because we want to correct the blinks. So we have to go one step up in the tree to the new reference node and apply our Ocular Correction here. And I will open it. Okay. Let me mention, though, it is generally recommended to screen and mark your data for artifacts before ocular correction. I mean artifacts other than ocular ones, because they might otherwise interfere with the regression. However, as there were no large-scale high-amplitude artifacts in this data set, at least we didn't see any when we scanned the data, I will skip this here. It can also be beneficial to apply a high-pass filter before ocular correction. Large offsets might otherwise have a negative effect on ocular correction. We have done this already, though, because we filtered with 0.1 Hertz, so I do not see any further actions necessary here. Let's check the parameters that we have to enter. So we have to enable some EOG channels. We can use vertical and horizontal EOG. We don't have to use both, but we can, and we will actually. So I enable both of them. You see the ocular channels down here in the list of channels, and as said already, we have 4 dedicated EOG channels. I have 2 vertical ones, the VEOG-U, which was recorded from above the right eye, and VEOG-L, which was recorded from below the right eye. I have 2 HEOG channels as well. They were recorded from the outer canthi of the left and right eye. It is generally recommended to use dedicated EOG channels with ocular correction. If you use sculpt channels instead, it can happen that the correction is either insufficient or that too much is corrected and you regress out some real brain activity. Okay, I will use for the VEOG channel the VEOG-L, and I also want to use the VEOG-U, and I will enter that as reference channel. So that means these 2 are referenced against each other. Let me mention, if you have only 1 VEOG channel, for example, you recorded and your 2 bipolar VEOG channels were already fused into 1 VEOG channel, or you did it manually in Analyzer before ocular correction, then you still can do that. Instead, then use the common reference option and enter this VEOG channel here. I do the same for the HEOG, and I will select HEOG left versus HEOG right. In fact, it doesn't matter if I put the left one here, the right one here, or the other way around, and here as well. This comes out to the same result. Okay, since we do not have blink markers yet, I need to select by algorithm because we need to detect them. And it's also important now that I do not enable write-only markers because I really want to have a correction in the end. Then it's still necessary to select channels, and I will just enable all of them, and I click OK. Okay, that goes fairly quickly as well. Let's check the result by creating an overlay again of the corrected and uncorrected data. So I drag again the data from the new reference node in here, and I will select some less channels, some fewer channels here. And as you can see directly, the black line is now the corrected data, the red line is the data before correction, and there is definitely some difference. So the blinks are much suppressed. Okay, let's now see what was the effect of ocular correction on our deviant tone ERP. In the end, we did this to lose less trials, right? To investigate this, I will use the history template function in Analyzer and take our processing tree from the raw data inspection and just drag and drop that onto my ocular correction node. It will quickly open again the raw data inspection interactive view. You can see on first glance there is much less color down here, which is probably why there are no blinks anymore. I just click OK for now and let the template run through. And here I already have my new average deviance. And what you can now do is just simply check again the operation infos. And what do we have here? The number used for the average now is 24. Okay, so that means we are now down from roughly 56 to 20% of trials lost, and this is quite an improvement. Let's anyway quickly look at the raw data inspection after ocular correction just to see what is different now. There is still some data marked as bad, but not EOG related. Maybe there are still, as here, for example, some residual EOG artifacts. I will now ascribe that to me being not so strict, because I also didn't do any raw data inspection before the ocular correction here now. My recommendation to you is, if you scroll through your data after ocular correction and you see there is residual EOG in there, either go back to the ocular correction and check it, or even go beyond that and check the pre-processing before. Maybe you missed some artifacts that should be marked, and that will in the end lead to better results. Okay, generally it makes sense to consider such strategies to attenuate artifacts by mathematical means, unless you have a very large number of trials where you can easily tolerate to lose a couple of them. However, more trials means also a longer recording time, which also means that there are potentially more artifacts. In the end, a very similar situation could come up as well with large trial numbers. Good, now that we have our ERP to the deviant stimuli, what's missing is the ERP to the standard stimuli. To get there, we need to create a second analysis branch starting from our segmentation. We can do this very quickly by right-clicking on our existing segmentation for the deviance and selecting Edit Parameters Copy. By doing so, the dialog of the segmentation for the deviance is opened with the same parameters entered, but now I can change them, and because I selected the copy function, it will then, with these changed parameters, create a copy of the branch. And the only thing I need to change actually is the reference marker. So I need to take out the deviance and put in the standards. Everything else I leave the same because I want the same length for my segments. I click finish, and that thing runs through, and there is already our average. Okay, what's important now to distinguish this from this, because you see now you have 2 average deviants, actually you have 3, is now to do some bookkeeping. So I will rename my notes. This one is my segmentation to the standards, and that one is my average to the standards, and that one, the average to the deviance without ocular correction, I will actually delete so that I'm getting not confused that I have 2 of these notes. Let's now inspect the ERP to the deviant stimuli again. I will for now close all windows that are open because I have so many views open, just that it's a bit tidier. So I double click again on average deviance, and let me now show you the butterfly view by right clicking, switch view, and selecting butterfly view. That's something you saw already earlier in my slides. And it's a very nice way of inspecting your ERP because you get one single trace for every channel. And if you go through the channels, you see they are highlighted in yellow, and also you see the corresponding channel name up here is highlighted in a box. It also works the other way around, so you can nicely identify which trace is which channel. I will click on the VEOG and HEOG channels, and they are then taken out of the display, so I only see sculpt channels. And what I can do again now is also here that I can do some topographic mapping. I could again mark this positivity around 300 milliseconds. What I can also do is just marking a little bit less data and shifting that through the data. So you can live and nicely inspect the topography, how it's changing over time for your ERP components. Okay, we saw again here, so here we are in the middle of the P300. It's again like in the old deviance node, rather centroparietally and rather around the midline distributed. Its peaks around 300 milliseconds. Let me say though, this doesn't have to be the case. ERP components can vary in latency depending on the group of subjects or condition you are looking at or the material used. So it still can peak around 350 or 400 milliseconds and be your P300. So this always depends on the data that you are looking at. Okay, let's close that, and via switch view again go back to the grid view. What you can now do, again, I highlight PZ. You can overlay now the average of the standards, now in red. And what you can now see nicely around the 300 milliseconds, we have this positivity in the deviance, and we do not have such a positivity in the standard ERP. This means for that subject, our oddball worked. It delivered the expected electrophysiological results. So that's a little bit like proof of principle here. Okay, one still is still missing to finalize the analysis. Of course, we would need to export now some key measures to use the output in statistical analyses. One thing that is often provided as a basis for statistics are amplitude or latency values of a certain ERP peak. However, to provide measures related to a peak, we would first need to identify the peak. And we do not want to do this by mere eyesight. For that, Analyzer offers you peak detection transformation. And you can find that up here, segment analysis function, result evaluation dropdown, and there it is. This allows you to automatically detect peaks within a specified time range relative to the reference marker. Okay, I will use automatic mode for now. Here's also semi-automatic mode as in raw data inspection, where you can also change what was detected. For the sake of time, I will now stick to automatic detection. I will search separately in every channel, and I will look for a global maximum. I click next, and now I have to enter a name for my peak, and I will of course call that P300 because this is what we're looking for, and this will then put a marker with the name P300 in the data. I put some search window times. I check within 200 to 500 milliseconds after reference marker. I take a little bit a wider window because I do also want to capture the peak if the P300 is a bit delayed. Then I have to check the polarity, so there's plus and minus. I look for P300, the positive component, so plus is right. I go to next, and then I select enable all and click finish. And here we are. So you see now there is on every channel a P300 marker, and that marker sticks now exactly to the position where you found a maximum amplitude within this specified time interval. And as you can see, we looked at every channel separately, so it's not at the same time. It's sometimes earlier, it's sometimes later. We're now one step away from exporting some data about our peaks. Therefore, I will just do the usual thing, rename my node, put deviance behind it, and we're clear. Please note that this unique naming, so especially if I would have also now the peak detection for the standards, is very important if you're exporting data. It should be ideally condition specific. Okay, you have probably seen already up here that we have an export tab. To export peak latencies, we can use the peak information export. This export in a multiple export group works across subjects. You can therefore export your peaks from all your conditions and all your subjects in one go to a single output file. As this tool acts across subjects, it is also not necessary to have any node activated to use it, and therefore I will again close all my views. Okay, let's open it. And let's enter the parameters. So the peak name is P300. And the names of the involved data sets, that means the history nodes where you have this peak detected, is peak detection, deviance. Please make sure when you enter these things here that you type them correctly, like the node is named and also like you named the peak. If not, you will get an error because the right information cannot be found. What you have to do now is to select the data sets. I only have one, so I add that. By the way, you can also, as I mentioned earlier, do this across conditions. So if I would have detected my peak in the standards, you could just write here, comma, peak detection standards, and then it would do it across both. What I do have to do now is select the options here. What I can do is override my default decimal symbol. I do not want that. I can export the mean value around the peak. So the mean value at the peak is always exported by default. Around the peak means I can say, please give me the mean of plus minus 5 points around the peak. So I will get a little bit wider interval. And what I check is to export individual latencies for each channel. So I get also the time of my peak. The name, I will just leave peaks.txt. And the folder is our export folder, the one that you defined when you created your workspace. I click OK. And let me check for that now. So here are my workspace folders, and I go into the export folder, and here is the new file peaks.txt. I will open that with some text editor, and what you can see in here now is this is for the P300 peak. Here are my files, so subject 1. If I would have exported from more than one, you would see one line for each subject, and then you get the columns for the channels. You see always here from which node, peak detection deviance, the channel, and you see that twice here because you have it once for latency. This is with the L in the end, and once for the amplitude, which is with the V in the end for voltage. And then you have one column for every kind of information. And because this is just coded in this table or matrix fashion in an ASCII style, you can easily open that in a lot of other programs, such as Excel, SPSS, R, or MATLAB. So using it for further statistical analysis is very simple. Okay, let's close it now. And actually, we're done now with our first ERP analysis. And I would say that was rather quickly, right? Let's therefore go back to my slides to recap what we did. So the first step was filtering. Filter settings should be selected according to the goals of the analysis, and the data quality may also influence the filter settings. Portions of data containing artifacts should be marked. These intervals will be ignored or rejected in subsequent processing steps. Check how many trials were lost after pre-processing. You can consider an ocular correction if your trial loss is due to a lot of blinks and eye movements. Always visually inspect all individual data sets and outputs. I know Analyzer does a lot of things automatically if you want to, so it's rather easy to ignore the data sets, but my recommendation is always check it visually, because then there are no bad surprises later. Inspect the resulting ERPs for latency, polarity, and topography, and export your measures of interest like peak information to finalize your results. Okay. That was the main demo part for today. I hope, though, that you are still all aboard, and I still want to discuss 2 more topics with you that can be very useful for your ERP analyses. Even though I'm not going to build another processing pipeline today, I want to demonstrate 2 further processing tools in Analyzer, and I will do that based on another data set, which is why I need to give you a quick tour about our cross-modal semantic priming paradigm, so you can get later all the steps that I will do. Okay, each trial consisted of 2 stimuli, the prime and the target. The prime was an auditory sound. The target was a picture because it's a cross-modal paradigm. Prime and target made up a pair. There were 2 classes of pairs, congruent ones where the sound and the picture matched, and incongruent ones where there was no match. Additionally, there was a task that subjects had to respond to by button press after they saw each pair. The task was only related to the target picture, as participants had to answer the question, does the object in the picture fit in a shoebox? There was a yes and a no button, and they should react as fast as possible. In the priming paradigm, the idea is that processing of the prime will affect processing of the target. It can be expected that congruent pairs lead to facilitated processing, as their semantic category matches. This can be higher accuracy or faster reaction times. Electrophysiologically, semantic priming is often used to investigate the N400. There are many studies that show that the N400 to incongruent pairs is larger than to congruent pairs, which is debated of being a consequence of the mismatch in semantic category. This effect was shown for a lot of stimulus materials. Just for completeness, here are again the properties of this dataset. I just want to point out two things here. The recording reference was an electrode on the nose. It's therefore pretty fine for the N400. This has usually a rather central maximum, and re-referencing should not be necessary therefore. The recording was done in 2 blocks with 80 trials each, and there were 50-50 congruent, so and incongruent pairs. So 160 trials, 80 congruent, 80 incongruent. And as you can see, the whole recording was done, it's much longer than the last one that we have, so a much longer paradigm. Okay, as I mentioned in the beginning, I already prepared the data processing tree for this ERP analysis, so let's check it out. And I will open, therefore, via expand all, this data set. On first sight, it looks not so much different from the Auditory Oddball. You have some common pre-processing, and then it splits up into 2 branches. Same here, because we have 2 conditions. Let me now close, though, the Auditory Oddball data, so we have a little bit more space here. The common pre-processing steps, again, contain filters, they contain raw data inspection, and they contain ocular correction. This time I used, though, the ocular correction ICA. The reason for this is that the semantic priming paradigm was recorded without EOG electrodes. This is usually not a problem for ocular correction ICA, but as I mentioned earlier, it might be for ocular correction, and therefore I used the other one. I will not go into any details of the ocular correction ICA today, as this is beyond our scope. If you're interested, please check out our tutorial on ocular correction ICA on our website. The tree is then separated into 2 subtrees based on the condition, congruent and incongruent. There is then an artifact rejection afterwards for checking for residual artifacts. So artifact rejection, by the way, is the same thing as raw data inspection, just for segmented data, raw data inspection for continuous data. Then we have here a second segmentation. I will say a little bit more about that in a second. And we end with the baseline correction again at the average. And then we have in the end 2 averages for our 2 conditions, and we can then compare them like in the Auditory Oddball, so same thing. About segmentations, I have decided to follow here a 2-step approach. This is just an example, you don't have to do it like this. My approach here was to do first a global segmentation where I wanted to get sorted all trials by condition, so congruent and incongruent ones, but I wanted to have all of them. And then I wanted to do a sub-selection of trials, and I wanted only to have the correctly answered trials, so that my ERP in the end will only be built up out of correct trials. And that I did in the second, more specific segmentation node. And to do this, I needed to use the advanced Boolean expressions that are available in segmentation. I will show you in the remaining time how this is done, and because it's a bit more complex, I have prepared a few slides to show you how the advanced Boolean expressions work. Okay, I try to make it as clear as possible with lots of examples. Let me show you first the operators that are available. There is first and last, there is cur, which is short for current, and there is step. These all serve to select a specific marker. Also, there are and, or, and not. They are typical logical operators. Here's in more detail what they are doing. First and last, either select the first or the last matching marker within a search window. Therefore, you need to specify the type and the description of a marker and a start and end time for the search window. In our example here on the right, you would select only trials where you have a response marker R51 within the time window 1000 to 2000 milliseconds, and this is in relation to our reference marker. And the first one found would be matched. Okay. The cur should select the reference marker, which is why you do not need a search window, only type and description. This operator is actually only necessary if you use more than one reference marker, and you need to make clear for the ABE to which reference marker it refers. So in our example here, you would constrain the ABE to the reference marker S30 of type stimulus. The step operator again works like first and last, but you can define a number of steps to jump to a marker in a certain position of a sequence of markers within a search window. The example that we have here is a little bit more complex because we have these asterisks in here, which are placeholders. So let me guide you through it. You would jump one step forward to a marker of any type, of any description, in a search window from 1000 milliseconds after the marker, reference marker, with open end, and at that marker you check for the description and you check if it's R57, and if it's R57 that trial will be selected. If it's not R57 it won't be. Finally, the and or not are used to combine all the statements above. You can also negate them with the not. And the example here just shows you have these two statements and they are combined with an or. That means either the first one has to apply or the last one, but not both. I know this might be quite abstract. I will show you in the next slides our specific example for the semantic priming, how to use all these operators there to make it a bit more clear. But you can also find a lot more information. For once, in the Analyzer user manual, there's a whole appendix chapter about the Boolean expressions like the syntax. There's of course also some information in the segmentation chapter, and then there are these nice two tutorial articles on our website where we show how to use it with concrete examples. Okay. Let's now check what markers we have in our paradigm and how to use them in our ABE. I cannot emphasize enough here how important it is to think of the markers when you set up your paradigm. Always think what markers you need and how you would code them appropriately. Otherwise, you risk to run into huge problems with segmentation when you analyze the data. So first of all, this is how a trial in our paradigm looks like. We have the prime followed by the target. Both are preceded by fixation crosses. After the target, there's a response time window. For the N400, actually, we do not need a time period around the prime. We would therefore reference our trials to the presentation of the target. And this is presented with a marker that tells us already if we are in a congruent or in an incongruent trial. In fact, though, it tells us even more because the marker codes also for the size of the target, which is important for the task later if it fits in a shoebox. So we have a marker for congruent big, congruent small, and the same for incongruent. Finally, there's the response period. It starts actually with the presentation of the target picture and extends up to additional 2000 milliseconds from the end of the target presentation. So 2800 milliseconds in total. And the markers code just if there was yes or no answered. As I showed you in the prepared processing tree, I have used this two-step approach. So the first global segmentation should already sort out the congruent and incongruent trials. And the second segmentation should then sub-select only the correctly answered trials. We will do this now with the ABE. We need therefore not only to consider the stimulus markers, but also the response markers. In my example, I will first focus on the congruent trials because it works totally analogously for the incongruent ones. So the task was, does it fit into a shoebox? You can answer yes or no. Obviously, therefore, big objects, you have to answer with no, and for small objects, you have to answer with yes. In the global segmentation, our reference markers need to be S30 and S31 because we want to collapse across all congruent trials. So we need the big and the small ones. We want to keep the segments as they are for the subselection in the second segmentation. Therefore, we should not change anything about the reference marker, and also we should not change the length of the segments. So also in the second node, we would again select S30 and S31 as reference markers. Then we need to check the response markers, and that means we have to repair reference markers with appropriate response markers. Trials starting with S30 should be followed by R57 in the response interval, and the S31 trials should be followed with R51 in the response trial if they were correctly answered. Okay, let's start with the first pair, S30 and R57. To clarify that the expression is just referring to the trials with S30 and not the S31 trials, we need to use the cur marker. So we say cur stimulus S30. And then we need to evaluate the response, and we need to check if R57 is in the segment. And we can do that by checking for the first marker in our response interval. So I check again for the type, which is response, the name, R57, and as search window, I use 1 to 2,800 milliseconds. So again, 2,800 milliseconds should be clear. This would extend the search window until the end of the trial. Regarding the start point, I recommend not to use 0 as a minimum time interval because this would also include the reference marker. It sits at time point 0. In some ABEs, not in all though, it can therefore happen if you choose 0 that the reference marker would also match the search criteria, and this might lead to faulty trial selections. I suggest therefore to start a search window at a data point after the reference marker. It doesn't have to be 1, it can also be 5 or 10 or whatever. So a little bit later, but early enough so you capture all responses. And here I will capture all of them because it covers the whole response period. Now I need to combine these two statements, and they should apply both, right? So and has to be in the middle of them. Now we need to do the same for S31 and R51, and it looks like identical actually. So the only thing to change is that the S31 has to go here, and here the R51 has to go. Everything else is the same thing. And now these two statements also need to be connected because it's at the moment just like two statements on their own. How do we connect them? Again with AND? Actually no, because that would mean a trial would need to fulfill the whole ABE. But that's just not possible because our trial only starts either with S30 or S31 and then comes the appropriate response. So it's not possible that a trial would fulfill both. And I think you see where this is leading, or has to be in the middle. And this is already the final advanced Boolean expression to select only the correctly answered congruent trials. Okay, let me show you quickly in Analyzer how it looks like there when you select this. To show you, I will just go to my segmentation ABE congruent correct node, so where I made exactly this subselection. I want to reopen the dialog, and I will do this by right-clicking and selecting Edit Parameters, Reprocess, even though I will not reprocess the node, but it's just a nice way to show you what parameters were selected. And I go directly to the second page, and here you can see what we did. S30 and S31 are selected as reference markers to collapse across all congruent trials. And then we have down here our advanced Boolean expression, and you can see what I entered here is exactly what was in the slide. So current stimulus S30 together with the response R57, or stimulus S31 and response R51. So it's kind of a scheme like A and B or C and D, right? Okay, so I will again cancel here because I do not want to change anything. Let's now check the effect the ABE has on the trial selection. So I open therefore first the segmentation congruent. As I said, all congruent trials were segmented here. Therefore, I have 80 trials in here. Importantly, in both segmentations, I did not use the the skip bad intervals option, so that I always get all trials. So my bad intervals are only dropped at the end when the average comes. Okay, so 80 trials in here, and then let's check the congruent correct segmentation. And here I have 67 trials. So that means out of my 80 trials, 67 were correctly answered. And then to finish, I check the average. Here again, I just see one trial, of course, but as you know already, you can check the operation infos and you see 59. So that means I had 67 correctly answered trials. Now 59 go into the average. So I had 8 trials that had bad intervals in them. Okay, that's all what I wanted to tell you about how to use the advanced Boolean expression in your segment selection. Let's therefore come now to our last topic of today. And as I mentioned, we have 4 subjects in here. They are all analyzed. Let me show you the second one. So same tree they're all analyzed on the individual level. And we can now use grand average to get mean ERPs for both conditions across these 4 subjects. Again, for grand average, it's not necessary to open any node because it acts across subjects. I therefore again close all windows. And I go to transformations. Again, segment analysis functions, result evaluation, and the grand average is in here in the drop-down. Okay, let me guide you through the steps. First, you need to enter the names of the nodes, and like in Peak Export, it's important here that you correctly type in here the names of the nodes that should go into the grand average. So in this case, our condition averages from the single subjects. Therefore, I write in here average congruent correct. I want to have 2 grand averages in the end, one for the congruent and one for the incongruent condition. I will therefore create a second line here where I put the same thing in, but then just change it to incongruent, and this one here I delete again. Okay, so whoop. Now I have to give a name for the grand average, and I will just call that GA for grand average congruent correct. And then I will again copy paste that down here and call that GA incongruent correct. Okay. Why do I have to give a name? Grand average will create new history files that contain the grand average, and they need, of course, to be named somehow. Let me mention you can also put a second condition in here. So you can write again, like in Peak information export, comma, and then the name of a second average. This is extremely handy if you want to average or to grand average across conditions. So if you want to collapse several conditions. What is very important here is that the naming is correct again, and also that now all your subjects fulfill these naming conditions. So the averages have to be called like that in all your 4 subjects. Otherwise, a single subject might not be reconsidered if you have like a typo in there. I will not use any of the options down here. Let me just mention you have again the option to create a standard deviation. And the only thing I need to do now is to select my history files. And I have 4 of them for the semantic priming, and I add them. And then I just click OK. And now it's done already. But where is it? It's not in here where all my subjects are, because it's across subjects. It's not in the primary, but in the secondary history explorer. And here you have the grand average files. So I open them. You have 2 raw data sets, and these contain now the grand average. Let me open not both of them, but just the congruent correct, and directly overlay it with the incongruent correct condition, which is now in red. And I pick out CZ because the N400 is usually rather centrally distributed. And here we go. So we have in black the congruent, in red the incongruent condition. And here we have like 400 milliseconds. So here. And as you can see, around 400 milliseconds, there are 2 waveforms going in the negative directions, both of them, but the red line is like the whole time above the black line, and this means it's more negative. We can clearly see that there are these negative deflections, more negative for the incongruent condition around 400 milliseconds, peaking roughly around 500, and then still this effect persists. And this is now very likely our N400, and it's more negative in the incongruent condition. So this is what we would have expected. It can also be that this effect is lasting longer. It can also be that this difference later here is due to other ERP components that come later. We don't know that yet, so this would require much more interpretation and thoughts. But let's not interpret too much here, because you know this is just 4 subjects averaged. So probably this will not yield any statistical significance yet. It's just a too small sample size. But it seems like that our experimental results point in the expected direction, so we are on a good way. Okay, that's actually what I wanted to present you today from a content perspective. Let me jump back to the slides and sum up the second part. Always make sure that you have sufficient markers coded in your experimental paradigm. And also that they are named appropriately to differentiate them. Please note, though, that it is also possible to have too many markers. That might be disturbing. You can, of course, delete those again offline in Analyzer and concentrate on the others. But it also makes sense to think of which markers are really needed at a time when you program your paradigm. The advanced Boolean expressions, or ABEs, are powerful in helping you to implement more complex segmentation schemes that consider conditional dependencies between markers. As we saw, you can, for instance, only select correctly answered trials. Make sure, though, that you use the proper operators and also check for the correct search window so you don't miss any trials or any markers. The grand average is usually the endpoint of an ERP analysis. I mean, of course, before statistics, that's a whole different story. Again, it is very important that you name your nodes identically across subjects and uniquely within subjects. Otherwise, grand average might get confused. I also recommend to have an eye on the properties of the single subject averages. I didn't discuss that earlier, but generally, of course, it's recommended to apply the same processing to all subjects. However, sometimes you might have to deviate from that rule because the dataset needs special treatment. Maybe there are channels that need to be removed. However, such property changes might lead to problems when you average across subjects, as those properties are matched, so between the files that you average together. If you therefore get any error messages by grand average pointing out that a certain dataset could not be used, consider checking them for their properties. They might differ from the remaining files. Okay, now it's the time to answer your open questions. I know we are already very far in our time for today. Sorry, it took maybe a little bit longer today. Still, I hope you can stay with us for our question session. If you have to leave, you can watch it, of course, offline later in the recording. But I would be happy if you're here and send me your questions. You can still send questions if you didn't do it yet via the chat window in your questions pane, and I will try to answer as many as possible. Please understand, though, if there are a lot of them, I might not be able to cover them all. Okay, let's check what we have. Okay, the first question here is, you showed the export of peak information, but I always export mean amplitudes from the fixed time windows. Yeah, that's often done in ERPs. So the question is, I have no peak marker, can I still do that? Yes, you can. Probably you think that because in the peak information export, you have to give this peak name, so you have to definitely detect a peak before. But we have also the area information export. In here, you can do what you asked. You can put time windows in here, starting from, ending with, like 200 to 300. And then you would get a mean activity in that time window, or you could get the area, so the area under the curve. You can do that for time domain. You can also do it for frequency domains, so like between 10 and 20 hertz or whatever. It works the same way. The output is also the same as for the peak information, so you can use it for statistics as well. Okay, let me check for the next question. Do I have to keep the same number of trials for all subjects? Of course not. I think actually, I mean, you can, of course, if it's possible. There might be paradigms where this is important. Of course, it's good if they do not deviate too strong. Because this might lead to weird results, because then the power might be different in the different subjects. So I also do not have the same number of trials in here, just because of the processing I did. Also, it's not possible because some data might be noisier than other data sets. In the end, though, they are roughly the same. And you should probably, if they are not always the same, indicate in your publication later how many trials went into each condition. This is usually something that is required. Okay. Then we have here, can you export peak-to-peak information in case of a baseline drift? You can export peak-to-peak information, actually not with the peak information export, because here you can only enter one peak marker. But I didn't talk about our solutions today at all, because pretty much everything you need for the standard ERP analysis is in the transformations. But you might know we have the solutions. You can download these from our website. They do not come with the installation of Analyzer. And in here, there are also grouped like the transformations, and there are a few export solutions. So let me just select one data set. I can open then the peak export solution. So it's called very similarly to the peak information export. Where is it? Sorry, it opened on the wrong screen. Now I found it. Okay, here you can in fact do what you asked for. So because here you can do peak, that would be like the same thing as in the other inform, in the other export, but here you have this peak-to-peak action. And if you activate that, you can also use two peaks. So then you just have peak 1 and peak 2, and then you can also get an export about the timing between them or the amplitude distance. Okay, now we have some more questions. How do I make an average ERP for several channels? I've tried using the pooling function. However, I can't overlay these pool channels to visually see the difference in the wave. The pooling function is the right thing, definitely here. Let me just, for those of you who don't know it, show it. So it's in the channel preprocessing. There we have pooling. You can say now, okay, so pooling in the kind of, I put together electrodes into like a region of interest, so like a ROI analysis. Let's say I want one new pool, then you can name that somehow, and then just by marking here, these channels will go in that new pool. I don't really get what you mean with you can't overlay these pool channels to see the difference now. Maybe you mean with the original channels, that should in fact be possible. So let me just create something. I just click like 3 channels now to create a new pool, and I will actually call it pool. I click OK. I get that in here. Okay, now I just have like my pool. Let me do it again with reprocess and take the keep old channels, because now I get the pool and the original electrodes. And now what you can do is that you just drag a channel onto the other one like this and like this, and then you make it bigger, and then you can see it. Maybe this is what you wanted to know. If not, please send us an email later, then we are happy to check it for you. I think though this might be maybe what you asked. Okay. What happens in the topographic view in case channels have been removed from the analysis? This is a very good question, actually. Because let me again open here something and open the mapping view. So this map is of course interpolated based on the channels that are here. So based on the coordinates of these channels. You also have to have coordinates. If you don't have any, you will get an error message. So in edit channels, you can see the coordinates of all your channels. And here you can also take out now a channel. So if you, let me just take out the frontal channels. So let me just take out these 4. I click OK. I have now less channels. And I will mark again some data in the mapping view, and then let me check that I right click here and say selected area settings. So just to compare, I want to have the same time window. So I take 300 to 350, and I take the same one here. It's actually not mattering in which channel I mark, because the topography is across all channels. 300 to 350. Okay, and let's compare. It looks very similar, but you can see there is something happening here in the front. Okay, yeah, I think it fulfills what I want to explain. If you take out channels, you don't see them here anymore. The topography is, of course, interpolated from the other channels, because you have only voltage values at each channel. You do not have voltage values in between, because you do not have measurement points there. So you have to apply some kind of interpolation between channels. You can see what is interpolated if you go to the settings of the mapping view. Here are all these interpolation settings, which means definitely if you take out channels, you will alter the maps. Therefore, if you are interested in the end to analyze only the results of your ERPs in a few channels, and you show only these channels as waveforms, still create your mappings based on all channels. Do not take out all other channels and create the map just on those. It will definitely alter the map, and it will not give you the real distribution of voltage across your whole measurement. Okay. Let me check. Okay, I still have one question here, which is a very short one actually. I don't have the segment numbers in the status bar in my analyzer. Why is that? Can I get it? That is probably referring to down here. Yes, please just make sure that your analyzer is maximized. because sometimes it's just like this. So maximize it. And if it's then still not there, it's probably not selected. So you can just right click down here and here make sure segment is enabled, and then you will see it. Okay, let me see on the time. I will maybe do some, yeah, I still think I do one more question, definitely. There is actually a nice one here. It was mentioned earlier that you could also have reaction time differences. I guess that was in the semantic priming. And I have a similar experiment, and I'm thinking to do that as well. Can I investigate that in Analyzer, or do I have to do that elsewhere? You can, of course, do it elsewhere. I'm sure your presentation software, so maybe Presentation or ePrime, they output, of course, behavioral files with all the reaction times. Usually they do as well, at least. You can do that in there, but you can do it in Analyzer actually. If you have markers for both the stimulus presentation and for the response. And also the response marker should have been sent at the time, of course, when the button was hit. Because sometimes you may send the marker like at the end of the trial at a fixed time, and then of course it would not work. Also here you need to use a solution. Let me just open a node. I take the baseline correction node here, so before my average. And here I have always my stimulus marker, and I have the response. The response marker is the blue one, and you can see from trial to trial it's at a different position because it's sent when the reaction happened, and therefore the time in between is an indication of our reaction time. We have a solution. You can download that from our website. It's called Right Markers. So it's in the markers subgroup. Let me quickly show you because it's fairly easy. Again, my solution opened here. Okay. So what you would have to do, you can select here which markers should be considered. I need to consider stimulus and response markers. They are already ticked because the solution detects them in the data. I want to detect certain parameters, so you can detect more parameters. The important one is the position, because the position is like where the marker sits, and it's therefore informative for the reaction time. If you're interested in reaction time, I would definitely tick this right marker position and point count as millisecond values, because otherwise you would get the reaction time in data points, which is usually not what you want to have. And then to structure the file correctly, so because it will always give you like the between two markers the time interval. So here you can in non-segmented data say when a new line should be written, and here you just say, okay, for each stimulus marker write me a new line, and then you get the stimulus marker and the response marker in one line with the reaction time. Just try it out. I know this sounds maybe a bit abstract now. I click OK. It writes it to a file, again to the export folder. By the way, in the solutions folder, you have the solutions help. Here you find small documentations about every solution because they are not documented in the user manual. And again, so in my export folder, I have now this semantic priming file. It's just an ASCII coded text file, so I open it again, and now you have it here. So I'll make it big again. We have now here the stimulus marker. It says always 200 here because it's at the data point 200, because it's we have minus 200 to 0, and at point 200, which is time point 0, there's the marker. Here are the markers, and then the response markers, and then it tells us here in milliseconds the time in between. So you can use Analyzer under these conditions to get reaction time results. Okay. We are now over time already a bit, and I think I'll stop here. Thanks for all your questions. Let me just finish the whole session now with going back to our goals that we had initially. I wanted to give you an overview of the analyzer transformations that you will most likely use if you analyze ERPs. Of course, there's a lot more, but I think we covered all the basics that you would need for an ERP analysis. I also wanted not only to give you an overview, but also to demonstrate how to use these transformations. I hope I achieved this goal with my example paradigms. They were, of course, fairly easy ones. I'm sure many of you use more complex stuff, but I hope that you could still profit from checking these pipelines together with me. Our learning outcomes for today were that you get to know the available tools and also that you learn how to export data for your further processing outside of Analyzer, may it be statistics or additional graphic processing or whatever. Where you find more information, let me finish with that. Of course, the Analyzer user manual, you can find it in Analyzer via the help tab and also on our website. Also, we have a lot of press release articles and support tips on our website. Then, of course, it's always great. By the way, the links to these support tips that are useful are also in our handout of today, so you might have seen already. It's always great to start with textbooks covering EEG processing. We very much recommend the Steve Luck and Todd Handy ERP books. They are both great, especially for introduction and for starters. Of course, it's always the best idea to go to literature of your own field, because there you see best what is done processing-wise with data similar to your own experiment. But there are also guideline papers out there that help you with ERP and EEG research in general, as they give a nice overview of things to keep in mind. So when you design, when you record, analyze, and publish your data. And with that, I'd like to close the webinar. I had a great time. I really hope you did as well, and it might have stimulated your own ideas for ERP analysis. Sorry that we ran a little bit late. I hope it's still fine for you. Thank you for your participation and attention. You will receive the follow-up email with the link to the PDF slides again and also to the video recording roughly in 1 hour. A survey is also available directly after the webinar and also in the follow-up email. We would really appreciate if you have a few minutes to complete our survey. It doesn't take long. If you have any questions about the content of this webinar or any other topic around Analyzer, please contact us via our support email, support@brainproducts.com. And on behalf of the whole Brain Products family, I wish you a very nice day. I hope to see you again in one of our next webinars. Goodbye and happy data processing.